All right, let's take a look now at section 5.5, and let's talk about exponential functions and bases other than e. In previous sections, we've talked about the exponential function of base e, also called the natural base. That number comes from the natural logarithm function. It is the number that serves as an argument of the natural logarithm to give us a value of 1. Or in other words, natural log of that number is equal to 1. And we've noted all kinds of nice properties of the exponential function with a base of e. Namely, it's its own derivative, which means it's its own antiderivative. It exhibits all sorts of nice properties of exponential functions that we've known since algebra, and it has a nice infinite domain with no asymptotes or discontinuities. So here what we want to do is we want to look at what happens when we have a base other than this specific number, e. Okay, well, how do we define that? Well, let's go ahead and do that. Now, it's important to define the exponential function with a base of something other than e using this original definition, using this original function, because we know a lot about the exponential function. If we define 2 to the x or 3 to the x in a way that has nothing to do with the exponential function of base e, we're starting all over again. We're having to redevelop all of our properties and all of the things that we know about the exponential function, but if we use this in our new definition, it'll inherit a lot of those same properties. Okay? So let's see here, the definition. We're going to begin with a value of a, that's going to be the base of our function. Let a be a positive real number, no negatives and no zero, other than the number 1. So you can have any positive number, not 0, no negatives, and the only other number we're excluding is the number 1. Let x be any real number you like. Let x be a real number. No restrictions there. Okay. Then we're going to define an exponential function as follows. A to the power of x is going to equal to e to the natural log of a times x, like this. This defines the exponential function of the base a. Okay. We're going to develop a few things about this new exponential function of an arbitrary base. But before we do, let's talk a little about what the definition says and what it restricts. So first of all, we want to say, okay, let's make sure that a is not equal to 1. You say, well, why not? Well, if it's equal to 1, note, if a is equal to 1, then we are left with 1 to the power of x, which is equal to e to the natural log of 1 times x. And either way, 1 to the first power, 1 to the second power, 1 to the third power, 1 to the fourth power, 1 to the any power is just the number 1. If you look at it using this expression, the natural log of 1 is 0. 0 times anything is 0. And e to the 0 will always be 1. So here, regardless of how you want to look at it, this is not ever going to change. It's always a constant value of 1. So here we wish to exclude a base of 1, not because it's impossible to use, but because it's, well, frankly, a little boring. This is not exponential or anything other than a constant. So we exclude that one. So it's not that the number 1 can't be used, it's that we don't really classify it as exponential. It's constant. Okay. Now, why do we want to define it this way? Why do we want to define it as a to the x equals to e to the natural log a of x? Okay, well, why we want to define it this way is because, again, we know a good amount of things to be true about the exponential function with a base of e. We know a lot of properties. We know a lot of algebraic properties, and we know a good deal of calculus of the exponential function with a base of e. So by relating this new function to the one we know a lot about, we can express our new results in terms of the old ones, which are things that we know how to do. Okay, so that's why we want to, but why can we? Like, how is this the same? How does this equal to this? Well, let's see. If you take e to the natural log of a times x, recall that there is a property of exponential functions, and you've seen this all the way back from algebra. This is not a calculus. This is not something that requires calculus to get, although we do see it in previous sections in this course, in the calculus series. But this is something that you've seen all the way back even in algebra. Recall that if you have an exponential function, a logarithmic function, let me use the same letters here. So b natural log of a. If you have the natural log of something and you're multiplying it by some value, that's the same as saying, oh, that's the natural log of a raised to the power of b. This is an algebraic property of a logarithm. Oh, okay, well, using that property, we can say, well, let's see here, e to the natural log of a times x. I could write that as e to the x natural log of a. I'm just using commutativity here. I can switch the order of multiplication. But now, this number can be brought up in the argument of the logarithm. So I can write this as e to the natural log of a to the power of x. But now recall that exponentials and logarithms are inverses of each other. They're inverse functions as long as you have the same base. Well, yeah, but this is an exponential function of base e, and this is a natural logarithm, meaning it's also in base e. So here, e to the natural log of a to the x leaves you just the argument of the logarithm. It's a to the x. Again, recall that because exponentials and logarithms are inverses of each other, e to the natural log of something is just equal to that something. So that's what we get here. All right? So here, you see the progression. E to the natural log of a times x is the same as saying a to the x. Okay? A third thing we want to mention here is, okay, well, we want this to be a positive number. Why no negatives? Well, note right here you have the natural log of a. We're going to use this to define this expression here. But recall that the natural logarithm doesn't have negative numbers in its domain. Recall, in fact, the simplest way to see this is with the graph. Recall the graph of the natural logarithm function. And again, this is something from algebra. Here you have the value, the point 1, 0. And the natural log of a, regardless of what a happens to be, is either going to look like this, assuming that your a is greater than 1, or, and here this is a greater than 1, or it's going to look like this if you assume that a is less than 1, but still greater than 0. Okay? Note that regardless of what your base happens to be, here you only have positive values. Oh, actually, I take that back. Here, this we wouldn't use this one here, because here we're looking at the logarithm of base e. So here your base is already assumed to be greater than 1. So here we wouldn't worry about this. So here this would be your base is greater than 1. So yeah, we don't worry about this one. In any event, notice that your domain is only from 1 to infinity. So here, the value inside the argument of the logarithm must be positive. So again, note the domain of the natural log of a is numbers from 0 to infinity, not including 0. So here, because the natural logarithm of a is used in this definition, we don't consider numbers outside of this domain. So here we want a to be a positive number. Incidentally, this restriction is lifted in later courses. Anyone who follows mathematics long enough eventually gets to do analysis of complex numbers, basically calculus, but with not real numbers, with imaginary or complex numbers. And then this relaxes a little bit. We actually do allow negative values, but that's something we can't see for quite a long while now. Once you define a exponential function with a base of a, you can now define a logarithmic function with a base of a. After all, exponentials and logarithms are inverse operations. They're inverse functions of each other. So if you define a new exponential, we need to define a new logarithm. So let's go ahead and do that. Definition. Let's begin with, again, a is a positive number that's not equal to 1. Let a be a positive real number. And again, that might be rescinded later on down the line, depending on how far you go in math. But as far as we're concerned right now, this is our domain. Right? So let a be a positive real number other than 1. Okay. And just like before, we're going to let x be any number we like. Let x be any real number. Okay. The logarithm, base a, of x, and that's how we're going to do that. We're going to denote our new base as a subscript of our logarithm. This is logarithm, usually abbreviated log. Log base a of x is defined as 1 over the natural log of a times the natural log of x. Or sometimes people prefer to write it as the natural log of x over the natural log of a. Just like that. So this defines for us the logarithmic function of base a. Okay. Just like we see with the exponential function, we want to go ahead and define our new function with respect to our old one. We want to define arbitrary exponential functions using the natural base exponential function. And likewise over here, we want to define an arbitrary base logarithm with a natural logarithm, one with a base of e. Note that this works out quite nicely for the following reason. We want that the log base a of a to the u is equal to u. Right? That's what we want. That's what we're defining. By defining a logarithm base a, we're looking to define the thing that is the inverse operation to the exponential of base a. Or in other words, we want log base a of a to the u to give us just that u. We want those to simplify out. Okay? All right, well, now u, I can multiply times the number 1, right? Wouldn't change anything. Okay, well, I could, but why would I want to do that? Well, maybe let me not use a boring version of number 1. Let me use a more interesting version of the number 1. If I multiply top and bottom by natural log of a, these together are the number 1, a number divided into itself. But now this can be rewritten ever so slightly. After all, we have a property that tells us that the natural log of a, if you're multiplying it times something, that something can come up in the exponent of the argument. So here we can write this as the natural log of a to the power of u over the natural log of a. But you'll now note that these two expressions are identical. A to the u is exactly the same as this a to the u. So let me take both of those and call them something simpler. Let's let a to the u be represented by something simple. Let's just say x. Then that means that the log base a of x is equal to the natural log of x over the natural log of a, which you'll recognize is exactly how we define the natural logarithm. Natural log of a, natural log sub a of x is natural log of x over natural log of a. So this shows exactly where we get that from, and it justifies its use. Note that because of the way they're defined, since the function f of x equals a to the x is defined in terms of e to the x, and let me use a different name here, g of x equals the log base a of x is defined in terms of the natural log function, natural log of x, then that means that we can expect a lot of these properties that we've had for exponential and logarithms to end up being inherited by these new functions. We will see the new functions inherit the same or similar properties. After all, if the logarithm base a is exactly the same as the natural logarithm of x, as long as I divide by the correct number, well, whatever is true of the logarithm, natural logarithm of x, is going to be true for the natural logarithm of a, except maybe for a little constant there. So let's see how that works. So let's see here, theorem. Your textbook will call this one a theorem, and it says it's the theorem about derivatives of bases other than e. Here, if it's a particularly important theorem, we'll name it. However, it's something just describing a property or a result of a simple computation. Generally, I'll just write theorem. All right. So here, theorem. There's going to be a few every once in a while that are important enough that we're going to say theorem, and we'll name it. For example, L'Hopital's theorem, Cauchy's theorem, Green's theorem in Cal 3, and so forth. But otherwise, I generally have a custom of just writing theorem. For those of you following along in your book, you'll note that they actually do give every theorem in their textbook a name. But here I'm going to forego that for some of the minor theorems that simply describe a simple property of a function. All right, so we're going to begin with a positive real number other than 1. So just like with the exponential and with the logarithm, let a be a positive real number other than 1. Now, let's take a function that's differentiable, something you can find the derivative of. We'll call that function u. So let u be a differentiable function of x. Right, u of x, so it's a function of x. Okay? Then the following properties are true. The derivative with respect to x of a to the x is the natural log of a times a to the x. So you'll recall that for the exponential function with a base of e, the derivative of e to the x is e to the x. Well, here the derivative of a to the x is a to the x times some constant. So they're similar, but not exactly the same. Hence my note up here. Notice that they will either inherit the same or similar properties. Here it's not exactly the same, but it's very similar. It's not its own derivative, but it's its own derivative as long as you correct it by an appropriate constant. Let me go ahead and write it down here. The derivative with respect to x of a to the u of x, now again remember u is a function of x, is going to equal to the natural log of a times a to the u of x. So just like we had above, right? The natural log of your base times your argument, right? A times a to your argument. But then, because this itself is a function, we have to invoke the chain rule, which tells us to now multiply by the derivative of that function. Here, you might be used to using u prime. However, here, since the expression is written in Leibniz notation here, I'm going to go ahead and write it in Leibniz notation here. That'll be times du dx. Some people prefer to write this as a to the u of x prime is natural log of a times a to the u times u prime. And that is also acceptable. I'm going to write these over here, I suppose. The derivative with respect to x of the logarithm base a of x Right? That's going to be, you'll remember that the derivative of the natural log of x is 1 over x. Here it's almost exactly the same. It is 1 over x, but we also need an extra constant down here. Because in fact it's the same extra constant. The natural logarithm of a, but now instead of multiplying by, we're going to be dividing by. It's going to be part of the denominator. Just like that. And the derivative with respect to x of the log base a of u to the x, well, that's going to look the same. It's going to be the natural log of a times x in our denominator. But now, instead of putting 1 right here, because we now have to invoke the chain rule, you have a function within your logarithm, we're going to be multiplying times the derivative of u, which we're going to go ahead and put in the numerator here. So that'll be du dx. Just like that. Or again, some people will prefer to write log base a of u to the x prime, which is the same as u prime over natural log of a times, oh, that should be a u, shouldn't it? Because our argument was u, not x. All right, so there we go. Here, I'm going to go ahead and prove one of these, and then the rest have similar proofs. Here, we begin by saying, all right, what am I looking for? Well, I'm looking for the derivative of a to the x. Okay, well, I don't know anything about a to the x. Well, you know its definition. Well, yeah, that's all I know. Well, that's good enough. Because a to the x is equal to e to the natural log of ax. Okay, so if I'm taking the derivative of this part, that's the same as taking the derivative of this part. So here, I can rewrite this as the derivative with respect to x of e to the power natural log of a times x. All right? Okay, well now I've gone from the derivative of a function that I know nothing about to the derivative of a function that I know how to take. I know how to work with e to the x, or really e to the anything. Here, if I take the derivative of e to a power, well, it's going to be e to the power again, isn't it? It's going to be e to the natural log of a times x. Oh yeah, but now I have to use the chain rule. Because of course the chain rule tells me that if I take e to a power and take the derivative, that's going to be e to the power again, but now times the derivative of that power. Okay, well remember, natural log of a is a number. It's like the number 5 or the number 1/3 or whatever. It's a number. So the derivative of a number times x is just that number. It's like saying, what's the derivative of 5x? It's just 5. What's the derivative of 17x? Just 17. So here the derivative of natural log of ax, well, that's just the natural log of a. So here that would be multiplied in like that. But of course we know that e to the natural log of a times x, this right here is the definition of a to the x. So we can now write this as the natural log of a times, and this thing right here becomes a to the power of x, which is exactly what we have over here. Natural log of a times a to the power of x. This one right here is just using the chain rule. So here, in fact, when we number them, let's call that one 1, 2, 3, and 4. So this is the proof of number 1. The proof of number 2 is just use the chain rule on number 1. Okay. Number 3 and 4, I encourage you to do those yourself. Here you would do exactly the same thing that I just did. You would say, okay, I want the derivative of the logarithm of base a. Okay, we'll use the definition. You can write this as the derivative of a natural logarithm of something, and then you'll work this out. And then, of course, this fourth one is just the chain rule on the third one. In fact, maybe try it now. Go ahead and pause the video and go ahead and work through number 3. See if you can find the derivative, and then once you have a result, once you've completed a proof, go ahead and unpause the video and we can go through that one together. Alright, so we'll take a look here. Number 3, we want to find the derivative with respect to x of log base a of x. Okay, well I don't know anything about log base a other than its definition. Well, you'll find that oftentimes the definition is all you really ever need. Here, note that, let's see, where did you go? Here we go. Log base a of x is natural log of x over natural log of a. So let's go ahead and write that. Finding the derivative of this is the same as looking for the derivative with respect to x of 1 over the natural log of a times the natural log of x. All right, that's one of the two ways that we commonly see the definition of the logarithm written. You either write it as natural log of x over natural log of a, or 1 over natural log of a times natural log of x. Same thing. But now, taking the derivative of this, we'll note that this is a constant, right? The natural log of a. A is just a regular number, right? A is a positive real number. So the natural log of a is just a number. And so 1 over the natural log of a is also just a number. And one of the nice things that we learn in Cal 1 is linearity. If you take the derivative of a number times a function, you can just pull the number out. So you write this as 1 over the natural log of a times the derivative of the function. The derivative with respect to x of the natural log of x. Oh, but I know how to do that already. That's something we saw previously in a previous section. The derivative with respect to x of the natural log of x, that's just 1 over x. So we can write this as 1 over the natural log of a times 1 over x. And when you multiply those together, you get 1 times 1 is 1 over natural log of a times x, which is what we were looking for. And of course, number 4 is just use the chain rule on number 3. You'll note that about half of the proofs that we'll be seeing throughout the course will have multiple parts like this, and usually you'll note that the proof will be something like, okay, for part number 1, let's go through all the details. For part number 2, yeah, it's just the chain rule. For part number 3, let's go through all the details. Part number 4, yeah, that's just the chain rule. So that's going to be something that we see fairly often. So as a couple of quick examples of this, let's go ahead and find the derivative of a few functions. So let's say d dx of, I don't know, let's say log base 3 of x. Let's start off simply. Just a simple argument of x. By our previous theorem that shows us how to find the derivative, we see here that the derivative of a log of a base a of x is equal to 1 over natural log of the base times the argument x. Well, here the argument is x and the base is 3. So that's going to give us a result 1 over the natural log of 3 times x. And there we go. Note that you do have to write those parentheses there. Without the parentheses, that's natural log of 3x, which is not what we have here. We have the natural log of 3 times x. It's like saying this is the coefficient of x. If you're going to get those confused, you may also prefer to write it this way, 1 over x times the natural log of 3. And that's less likely to become an issue. Let's look at another one here. The derivative with respect to x of, let's say, log base 5 of, let's say the cosine of x. Okay, so now we have not just a logarithm of a base, in this case 5, but we also have an argument that's something other than just x. Okay, so we'll be using the chain rule here. Again, the way this works is if you want to take the derivative of a log base a of an argument, that's 1 over the natural log of the base, which in this case is 5, just like it was 3 before, times the argument, which in this case is the cosine of x. But now, because this is something other than just x, it's a function in its own right, the chain rule now says, okay, now let's find the derivative of cosine of x, negative sine of x, and multiply. So this is going to now be multiplied by negative the sine of x. And now here we can simplify this a bit. Sine of x over cosine of x is tangent of x. There's a negative in front, so we can write this as negative tangent of x over the natural log of 5. Just like that. And that makes us happy. For an exponential, let's say, for example, d dx of, let's say 9 to the power of x. And again, using our results from our theorem that we proved, that's going to give us the natural log of the base, which in this case is the number 9, times the function itself, 9 to the x. All right? Again, if that's going to be an issue, if it's hard to tell, okay, what am I multiplying together, you may wish to write them this way instead, right? 9 to the x times natural log of 9. And for some people, that's a lot less confusing. It's a matter of notation. You'd be surprised how sometimes just a simple change in notation will make something go from being very difficult for you to get to something that's, oh yeah, that makes a lot more sense. Right? So here, if you feel more comfortable one way or the other, continue to use whichever one makes better sense to you. It's just like derivatives, Leibniz notation versus Newtonian notation, primes. So for some, for any problem, those are identical, but in some cases it just looks simpler. It's easier to understand one way or the other. So go ahead and try this one. We've seen 3 examples. Let's do the 4th one. Let's have you try 3 to the, what's a good function? Let's have you try 3 to the power 2 over x. Okay, go ahead and give that a try. Pause the video and use the results of the theorem that we had to find the derivative of 3 to the power 2 over x. And once you have a result, unpause the video and we'll go through it together. All right, from the results of our previous theorem, we note that e to a power has a derivative that's e to its power. Here we have some other base to a power, and it's going to follow the same pattern. The derivative of 3 to this power is still 3 to that power. But now, because this base is different than base e, we're going to need to multiply this expression by the natural logarithm of that base. So that's going to be times the natural logarithm of 3. Right? Just like up here, we had this times the natural logarithm of that base. But now, because this is something other than just x, we're going to need to use the chain rule. So now we're going to multiply that times the derivative of 2 over x, which is going to be, let's see, that's going to be times negative 2 over x squared. Remember, the derivative of 1 over x is negative 1 over x squared, and here the 2 is just a constant, which we can simply bring on down. And now let's see, is there anything that simplifies here? No, it doesn't look like it. Don't fall into the trap of multiplying these. I've seen people do that. They'll say, 3 to a power times negative 2. That's negative 6 to a power. Don't do that. That doesn't work that way. All right, this is an exponential. This is simply a constant. They don't multiply. So here, there's nothing really you can do about it. Just 3 to the power 2 over x times the natural logarithm of 3 times negative 2 all over x squared. And, well, no one ever said your answers had to look very nice, did they? But that's our result. And up here. Now, one thing you may recall is a property of a logarithm, or several properties of a logarithm, that you first see all the way back in algebra, and then we see them again in Cal 1. In fact, we prove them in Cal 1. So here, let's go ahead and recall. If you have, and this is true of any logarithm of any base, although you often see it with a natural logarithm, but it's true of any logarithm. If you have log base a of x times y, that's the same as writing log base a of x plus log base a of y. If you have log base a of x over y, that's the same as writing log base a of x minus log base a of y. And the one that we've already seen we used to our advantage in this section here is log base a of x times y is equal to log base a of x to the power of y. And we've used that one to our advantage using the natural logarithm in this section. We can use these properties to simplify some of our computations when we work with logarithms of any base. So for example, let's say we want to take the derivative of, let's see here. Let's say find the derivative with respect to x of log base 5 of 4 over x squared square root of 1 minus x. This is just one of the problems from our textbook, so anyone following along, you'll find that in the exercises at the end of the section. You'll find that about half of the examples that I do in these lectures are going to come from the exercises. The other half are ones that are related to those. These I didn't pull out of the textbook, but they're related to ones that you do see there. This one is identically one of the ones from our course, from our textbook. So here we could say, okay, well, let me just use this property right here and be done with it, right? I can write this as 1 over the natural log of the base, in this case 5, over the argument, which is kind of big, times the derivative of the argument, which is also really pretty big. It requires me to use the quotient rule, and then the product rule within the quotient rule, and then the chain rule within the product rule within the quotient rule. Oh, that sounds terribly, terribly unpleasant. But we can use these properties to our advantage. Note that if I have log base a of a fraction, that's the same as log base a of the numerator minus log base a of the denominator. And it doesn't have to be a literal fraction with numerator and denominator being constant. This rational expression will work the same way. So if I want to take log base 5 of this fraction, I can rewrite it as log base 5 of the numerator minus log base 5 of my denominator. And again, make sure you keep the base 5. Okay, so now at least I don't have to worry about the quotient rule anymore. There's no more fraction. Oh, but look, that product can be split up using this property. After all, the logarithm of a product is the logarithm of the first factor plus the logarithm of the second factor. So we can write this as log base 5 of 4 minus, here I'm going to go ahead and take this and separate it. Let me put that in brackets, just so we can highlight which came from what. This is going to be log base 5 of the first factor plus log base 5 of the second factor. Just like that. Here you can distribute your negative. After all, that negative applies to all of this. So we can write this as log base 5 of 4 minus log base 5 of x squared minus log base 5 of the square root of 1 minus x. Oh, so it looks like I don't have to use the quotient rule or the product rule anymore. Oh, but I can do one more thing. I said it as if I'm surprised, right? I picked this problem because it does show all three of these properties working at the same time. Note here, if I have a power, I can bring it out as a constant multiple, for example here. But notice that that's also true over here. After all, a 1/2 power is the same as a square root. So here I can write this as log base 5 of 4 minus, and bring that 2 out, that's 2 log base 5 of x minus this 1/2 power, same as a square root, can be brought out, and we can write this as 1/2 log base 5 of 1 minus x. And if all of these are equal to each other, then the derivative of this one must be equal to the derivative of all of these. But now the derivative of this one is nice and simple. Because after all, derivatives are linear, which means I can take the derivative of each one of these pieces, and then at the end stick the appropriate pluses or minuses in between. So let's go ahead and do that. This is a constant. Log base 5 of 4. There's no variable there. Log base 5 of 4 is a constant. Here, let's see, what is that? I'm going to pull out a calculator here. Not that it actually matters, because it doesn't matter what base we have, but it's equal to approximately 0.86. that number itself doesn't matter at all. It could have been equal to 1.5, 2.9, or 1,000,000.73. It matters not, because after all that matters is that it's a constant, and the derivative of a constant is, I'm hoping everyone said this out loud, right, and jumped out of your seat. The derivative of a constant is 0. Of course, is 0. So here, that derivative is going to be 0. So we don't have to write it, but I'll go ahead and write 0 here. Minus 2 times, okay, so the 2 is just there, the logarithm base 5 of x, which, given our previous theorem, log base 5 of x is equal to natural log of x over natural log of, in our case, 5. Okay, so that's times natural log of x over natural log of 5 minus a half, and then we'll do something similar here. That's going to be, oh, wait, that's not right. That's not right. I've read the definition. I want the derivative of this. So here that's going to be 1 over natural log of 5 times x. Basically, I wrote the definition of this without ever actually taking its derivative. So that should be 1 over natural log of 5 times x. There we go. That's better. And then same thing over here. We can write this as, okay, the derivative of a logarithm of something is 1 over that something. Okay, so that's going to be 1 over that something, which is 1 minus x. But now, because this base is something other than the natural base, we're going to have to now multiply the denominator by the natural log of that base. So that's going to be the natural log of 5. Like that. And now, note this is an argument that's something other than just x. So now using the chain rule, the derivative of 1 minus x, well, the derivative of 1 is 0. The derivative of minus x is minus 1. So that gets multiplied by minus 1. And so in the end, our result is, we're not going to bother writing a 0. That's going to be negative 2 over x times natural log of 5. Here, the two negatives become a positive, multiplied together. That's going to be plus 1 over, right? Negative 1 times negative 1. That's all positive 1 over these denominators. So we can go ahead and write this as 1 minus x times 2 natural log of 5. Which, yeah, this takes a bit of effort to separate this out, but all of these properties are algebraic. It involves nothing more than adding, subtracting. And then this is much simpler to work with because of the small arguments. Whereas this could be done directly from here to here, but because of the complexity of the argument, the use of the chain rule was going to be significantly more complicated than anything that we see here. So this is a result without having to go through a massive amount of use of the product rule, the quotient rule, and several iterations of the chain rule, which makes us happy. Note that since we now know how to take the derivative of exponentials and logarithms of a new base, that means that we also now know how to find the antiderivatives. Note, if we know that the derivative with respect to x of a to the x is equal to the natural log of a times a to the x, if these two things are equal to each other, that means I could take the antiderivative of both sides and still have the same result, yeah? So here I could say, well, the derivative, take the antiderivative, is equal to the antiderivative of this other stuff. Just like that. So if these two things are equal to each other, well, their antiderivatives will also be equal to each other. Well, yeah, but these can be simplified. After all, this is just the integral of dA sub x, or dA to the power of x. Over here, this is a constant, natural log of a. That's a function. It's got a variable in it. That's just a constant, so I can write that as the natural log of a times the integral of a to the x dx. After all, integrals, just like derivatives, are linear. You can pull out constants. Oh, but now the integral of the differential of a to the power of x by the application of the fundamental theorem of calculus, that's just a to the power of x plus some constant of integration, yeah? Oh, that's equal to the natural log of a times the integral of a to the x dx. Oh, but notice, if I divide both sides by the natural log of a, I get the following result. I have now isolated the integral from a to the x dx, and it's going to equal to a to the power of x over the natural log of a, plus a constant over the natural log of a. But see, the thing is, if you take a constant and divide it by the natural log of a, it's still a constant. So here we don't worry about what that constant is. We're just going to call it plus c. That happens a lot. Whenever you take a constant that you don't care what it is exactly, you just need to know that it's there. If you add or subtract or multiply or divide something by it, we typically say, well, if it's just a constant, if you add or subtract or multiply or divide by a constant, it's still a constant. So let's just keep calling it c. The way that you'll hear a lot of textbooks refer to it is you absorb the constant. There was another constant right here, but it sort of got pulled in and mixed with the constant that was already there. We'll say it absorbs the constant. But in any event, here you see the result that the integral of a to the x dx is a to the x over the natural log of a plus a constant of integration. So for example, I almost want to call this a proof of something, but I mean really it's just we're using a theorem that we already knew mixed with another theorem. I mean, I guess you'd call it a proof, but I'm just going to go ahead and say, hey, notice that this is true. So as an example, let's say we want to find the integral of, let's just start simply. Let's say 2 to the power x. From this result, we see that, okay, 2 to the power x dx, we're going to integrate that, and that's going to give us, well, we're still going to get that same integrand, 2 to the power x, over the natural log of that value a, or in other words, the natural log of the base, which is just the natural log of 2, plus some constant of integration. Note that substitution and the chain rule are still in effect. So, for example, you might have something like the integral of, let's say, 2 to the sine of x times the cosine of x dx. And of course here you would say, well, look, that's the derivative of that one, right? The derivative of the sine of x is the cosine of x. So using substitution, the u substitution that we see in previous sections in Cal 1, we say let u equal to the sine of x, which means du is equal to the cosine of x dx. It's a differential. So here we can rewrite this as the integral of 2 to the power, well, sine of x, we're now just calling that u. Cosine of x dx, well, that's just du. And so now this result, it's going to look the same as this, except instead of x's, we have u's in there, right? So that's going to be 2 to the power of u, it's the same as this, divided by the natural log of my base, which is just the number 2, plus a constant of integration. But of course, u is a stand-in. U doesn't really mean u. U means sine of x. So in the end, we get 2 to the sine of x over the natural log of 2, plus a constant of integration. And that's our result. Okay. To close off the section, we are going to look at one more property of exponentials of base e, and in particular, we're going to be looking at a property that is used a lot in applications. This is used in economics, in biology, and biological systems, and so forth. Let's take a look at a limit that involves an exponential base of e. So let's see here. We'll call this a theorem. The limit as x approaches infinity of 1 plus 1 over x raised to the power of x, which is also sometimes written as the limit as x approaches infinity of x plus 1 over x. Here all they did was they found a common denominator. They wrote this as x over x plus 1 over x, and then they combined the numerators. X plus 1 over the common denominator. These mean the same thing. Either of these limits is equal to the value of e. Okay. This is something that appears in applications, and in particular it shows up a lot in biology and in finance. This is something that you'll see when you look at compound interest. Anyone interested in finance and economics, you'll note that the compound interest formula is essentially your initial principal plus some rate divided by time raised to a number of compounding periods. If distilled down to a simpler form, it looks like this. Right? So the compound interest formula is sometimes rewritten in what's called the continuous interest formula for a significantly high number of compounding periods, which is in fact an exponential expression. In chemistry, it's used for a similar reason, and in biology, it's used for a similar reason. Namely, you have something that's happening over and over again, and eventually it reaches somewhat unexpected equilibrium. Also, one of the reasons why this is called the natural base, because it tends to show up in a lot of natural systems, namely biology and chemistry. So here, let's go ahead and show that this is true. Let's begin by saying, and I'm going to go ahead and use this form. Let's go ahead and begin by saying that this is equal to some value y. We don't know what y is, but we're going to try to figure that out. So let's let y equal to the limit as x approaches infinity of 1 plus 1 over x to the power of x. Okay? I'm going to use this form. Either one will be fine. Okay, well now let me take the natural logarithm of both sides of this equation. Okay, so that's going to be the natural log of y. Okay, well if I take the natural log of one side, I take the natural log of the other side. The natural log of the limit as x approaches infinity of of 1 plus 1 over x to the power of x. Getting ahead of myself here. Like that. Okay, well now, here, taking the natural logarithm of this limit is the same as taking the limit of the natural logarithm. So here I'm going to write this as limit as x approaches infinity of the natural log of 1 plus 1 over x to the power of x. Incidentally, swapping these is only valid because this is defined. This limit exists, and you can swap those. Right? So that's something that's not automatically true, but it's true for this for what we often call nicely behaved limits, meaning limits that actually do exist and converge and everything else. So here, this is equal to this, and now because of one property that we saw just a few minutes ago, we can take this and just bring it down. So we can write this as the limit as x approaches infinity, and now you saw why I wanted to write x in the front, because that's where it ends up. X times the natural log of 1 plus 1 over x. Okay? So now, I'm going to write this in an unusual way. I'm going to say, okay, instead of writing this as natural log of 1 plus 1 over x times x, multiplying by a number is the same as dividing by its reciprocal. If I have something and I want to multiply times 2, that's the same as dividing by a half. Multiplying by a number is the same as dividing by its reciprocal. So here, I'm going to rewrite this in a slightly unexpected way. I'm going to write this as the natural log of this divided by 1 over x. Which, take a moment to convince yourself that means exactly the same thing. Oh, my apologies, I forgot to write the limit here. That should be limit as x approaches infinity. There we go. So now they mean the same thing. All right, now, notice I have 1 over x and 1 over x. Those are the same. So I'm going to use a substitution here. I'm going to say let t equal 1 over x. Why t? I just need a different letter. I'm going to say t is equal to 1 over x. Okay, well, as x approaches infinity, what happens to 1 over x? As x becomes infinitely large, 1 over x becomes smaller and smaller. So in other words, as x approaches infinity, 1 over x approaches 0. Oh, but t is equal to 1 over x. So that means t approaches 0. Right? If x gets bigger, the reciprocal gets smaller. So that's going to get smaller, but it has to stay positive. Notice all of these are always positive. 1 over positive numbers. Oh, so it's the smallest possible number you can imagine. Oh, so it goes to 0. So here we can write this as the natural log of y is equal to the limit as t approaches 0 of the natural log of 1 plus t over t. Like that. I've replaced that with t, replaced that with t, and now my limit looks like that. And now I'm going to rewrite this again in a maybe unexpected way. Limit as t approaches 0 of the natural log of 1 plus t over t. I'm going to go and subtract from this numerator the natural log of 1. Now at this moment you should probably protest and say, well, wait a minute, you can't do that. Whenever you do something to the top, you got to do the same thing to the bottom at least, right? You just randomly change your numerator. Well, no. Remember, the natural log of 1 is equal to 0, right? That's something from algebra. Right? The natural log of 1 is equal to 0, right? In case you didn't believe me. Okay, so here I subtracted 0. Okay, I guess that's allowed. I'm allowed to add or subtract 0 because it doesn't change anything. But now what? Well, what does that have to do with anything? Well, look at that. What does that look like? Think back to Calculus 1. Pause the video for a minute if you have to and try to think, what does that look like? And be specific. What is that? Pause the video if you have to and see if you can work your way through what that's supposed to look like and what that result of that limit should be. Once you think you have an answer, go ahead and unpause the video and we'll finish it off. We only have just a little bit left to go on this one. Okay, did you recognize that? It's a derivative. This is f of x plus h minus f of x over h. Okay, so maybe I misled you with the letter t here, right? It might be a little more recognizable if instead of t here, maybe we could have used the letter h. It doesn't really matter what letter we use here. So if we use the letter h, maybe it's a little more recognizable to you. You have a function of x plus h minus that function of x over h. That's a derivative. And here my function is the natural logarithm. So this is actually the derivative of the natural logarithm. Oh, but here I don't have x. I have the number 1. Oh, that means take the derivative of the natural logarithm and then plug in 1. That's what this is equal to. This is the natural log prime of 1. Oh, well, we can do better than that. Natural log prime. We know the derivative of the natural log. It's 1 over x. Oh, yeah, but we're plugging in the number 1. Okay, so then it's 1 over x, right? The derivative of the natural log of something is 1 over that something. But since here we're taking the derivative of the natural log of 1, then that denominator is just the number 1. Oh, but that's the number 1. 1 over 1 is 1. So now we end up with the natural log of y is equal to 1. And I'm out of paper, so that means I better be almost done, right? Let's exponentiate both sides. E to the natural log, so if natural log of y is equal to 1, then e to the natural log of y is equal to e to the 1. But again, as we've seen, since these are inverses, that'll leave me just the argument. Y equals to e to the 1. Anything to the 1 is itself. So this gives me y is equal to e. Oh, but y was that to begin with. Okay, so that to begin with is equal to e. And that was our result. The limit as x approaches infinity of 1 plus 1 over x to the power of x is equal to e. And that's it for the section. In the next section, we'll actually see a little bit more about limits, and we'll see some nice ways of computing some limits which are maybe a little bit simpler than this, because throughout this course, and especially in Chapter 9, we're going to be using limits to some new to establish some new types of results. In the meantime, if anybody has any questions, comments, or problems, please make a note of them. Obviously, you can't ask questions through a video. This has been pre-recorded, but you can reserve your questions. Make sure you write them down so you remember what they are, and ask next time. Next time we meet, the next time we have one of our class meetings or office hours, and make sure you reach out and ask questions as you need to. I hope everyone has a nice day.